Okay, so as I mentioned before, we gave you a few examples of systems, many systems, or major devices that we use in engineering systems, such as the nozzle, the diffuser, and the turbines, compressors. And I believe we solved this example. And really, I recommend you, I strongly advise you to go through this example, because this is really a major application of energy balance of an open system. And it covers most of the energy balance equation requirement. So please go through it. But I don't know if you have done any work on this, or you have any question about this example. But let me go through it quickly so you remember what we mentioned last week. So this is sorry, I didn't share the page, I believe. So this is the example that we solved last week. And I will go through it quickly again, because as I told you, it's quite important. I need you to understand the way to solve this type of questions. So as you know, the steam turbine is a major component in the power plants. And as you know, when we apply or allow high pressure steam to enter the turbine, what will happen here, it will rotate the shaft of the turbine, as you can see here in this example. So this shaft will be rotated under the effect of high pressure of the steam, and the energy of the high pressure and temperature steam will be converted to mechanical work here. And the remaining steam will leave at the exit, as you can see, at lower pressure and lower temperature. So first of all, in this type of questions, if you have all this information of the inlet fluid and exit fluid, the first thing you do is to get the values of enthalpy, of the inlet and exit, so that you can solve the question or solve the energy balance. And as you remember, in the energy balance equation, the first thing you need to do is, for every question, the first thing you need to do is to write down the energy balance equation, so that you know which part of the energy balance equation you can remove. So for example, you always say like this, you say Qn plus Wn plus the internal energy of the fluid, inlet fluid. So we said in this type of, because it's an open system, then we can say m dot open brackets h of the inlet fluid plus the kinetic energy, so V1 squared divided by 2 plus potential energy Z1, GZ1. This must equal the other side, which is the exit. So everything here should be the same, but at the outlet. So Q out plus W out plus all internal energy, the H exit or H out plus the velocity square over 2 plus Z, GZ2. Okay. All right. So now after we write this equation, you can ask yourself, is there any heat out or heat in? Is there any Q leaving the system or entering the system? As mentioned in the question here, there is no heat in and out, correct? So you can eliminate this, these two terms. Do we have any work input to the system? Anyone can help me? Is there any work input to the system, W? Do we have W in to the system?
No.
No, correct? So there's no W in. So I can remove this as well. Do we have W out? Yes, because this is W out. There's a shaft work here. So I have to keep W out. And for example, all the velocity and Z. So we have Z, we have velocity here in both sides. So I have to keep them. Although I know that these terms are quite small, but I need to keep them. So I can then reduce my equation to only W. So W out will equal to m dot, because the mass will be the same in and out, multiply by delta H plus the delta V square over 2 plus delta Z, delta GZ. Yeah. So this is my equation. This is my energy equation after I reduce the other one, the first one, because this is what I have now. Only the work represented by the change in internal enthalpy, and change in velocity and change in potential energy. Okay, so this is my final equation. So I can use this equation and solve the problem. Right? Is it clear for everyone? Okay. All right. So then let me clear this now. So now this is what we actually need to do. First of all, as you can see here, we used table A6 and we found the value of, because we know that this is superheated steam, the inlet superheated steam. I go to the table A6 and then I can find H1, because this is what I want. H1 is in the equation, the energy equation on energy balance. I need also H2. H2 here can be, we know that H2 is two-phase. The steam phase at the exit is two-phase because, as we said last time, how do we know that it's two-phase? Mervin, how do we know that this is a two-phase at the exit? There is a property that you can tell this is a two-phase. Mervin, can you hear me? Mervin, William, Bakhtiar.
Yes, sir.
So how do you know the exit is two-phase?
I'm not too sure. I wasn't here last time, but I would say because it's lost its energy.
No, you know, this part of the equation, this part of the system, the
Yes.
exit one, there is a property here that you can tell this is a two-phase. There is a property that tells you that there is steam equality, which is the X. Okay, if you have X less than 100 or less than 1 in the ratio, you can tell that this is a two-phase. Okay, right? Bakhtiar?
Yeah. Okay.
Yep. So once you find that, once you see that there is a X at the exit, you know that this is a two-phase fluid, then you have to apply this equation. So this equation requires the table, you need to go to the table A4 or A5. Since we have a pressure, then we can go to table A5, and you can get the value of HF and HFG from the table, and you know the X value, then you can find H2. And after that, the other parts of the energy balance is quite simple. So once we know the H1, H2, you can find delta H, and also you can find delta K from this equation, and delta potential, you can find it also. You can tell that it's these two values are very small compared with the delta H. All right. So this is how to solve this question. I don't want to take too long in this, and you can finish the other part of the question. Now, the other system or devices we didn't talk about last week is the throttling valve, and the throttling valve are it's a very simple device. It's flow restricting device. So if you have, let's say, a valve in the middle of a pipe, we call this a throttling valve, or we have a porous plug here, like this one here, that opposing the flow of the fluid, then this will cause pressure drop in the pipe. We call it throttling valve. And this equation, when you apply the energy equation or energy balance, it's very simple here, because you can eliminate all these parts. There is no work, there is no heat in, there is no heat out. Even the delta Z is nothing, but you can end up with probably delta H and delta V. Okay, so again, it depends on the property, or depends on the state of each fluid, and the the values given in the example or the question. You can eliminate all the terms that you don't need or you don't have the information about. Okay. Any question? Right. So go to the heat exchangers. Heat exchangers, as you know, it's a device where we have two moving fluids. So we have two different fluids. For example, in this drawing, we have fluid B and fluid A. So this is fluid B, and this is fluid A. And fluid B enters with high temperature. Fluid A enters with lower temperature. So you can see here, fluid A enters with 20 Celsius. Fluid B enters with at a temperature 70 Celsius. So fluid B higher temperature than fluid A. So we're gonna exchange, or what we expect here, there is heat transfer from high temperature to lower temperature. Yeah. So the heat transfer will be from the fluid B toward fluid A across this pipe. So there's a pipe here. So the heat will flow through the pipe to fluid A, and fluid A then will leave at higher temperature at 50. Okay, so this is a simple form of heat exchanger. Okay. Again, you can apply the same equation, same energy balance equation, right? And you eliminate all the parts that you believe they are not existing here, and reduce the equation to a simpler form, right? Okay, so let's take an example here. This example about the heat exchanger using two fluids. So there is a fluid which is the liquid water. So water entering the heat exchanger at 15 Celsius, and the same water leaves the heat exchanger at 25 Celsius. In the other side, the other fluid is refrigerant R134. Enters the heat exchanger at 70 Celsius and leaves at 35 Celsius. So we are cooling the refrigerant, and in the other side, we are heating the water. Yeah? Is it clear?
Yes,
okay.
sir.
Okay. So now the refrigerant enters the condenser with a mass flow rate given here 6 kilogram per minute, and the pressure of this refrigerant is also given 1 megapascal, and temperature is 70 Celsius. And the same refrigerant leaves, as we can see in the drawing also, leaves at 35. So all this information given for the refrigerant. In the other side, the cooling water, we know the pressure of the cooling water giving pressure, and we know the temperature inlet and exit of the water. That's good. But we don't know the mass flow rate of the water. So we need to find the mass flow rate. Okay. Here there is an assumption. They said neglect the pressure drop, which means the water enters at 30 kilopascal and also will leave. If there is no pressure drop, then it will have the same pressure at the exit. So the pressure at the exit will be the same, 300 kilopascal. Okay, so that's also given. So we know this information. Now, again, you have this equation. You can apply it here. Let's check what we can remove or what we can eliminate from this equation. Can we eliminate the work in and work out? Is there any work in and work out? Jenshi?
No, sir.
No, good, thank you. So there's no, we can eliminate these two. Is there work, sorry, there is any Q in, let's say from outside, or Q out, Q out? Is there any Q in, Q out here? As you can see, the heat exchanger, they put some insulation around it, which means when you have insulation, meaning that heat cannot be transferred or from or in or to the heat exchanger. So do we have then Q in and Q out? Christopher? Christopher? Christopher?
So,
do we have Q in and Q out from what you see from in the figure? Like Q in and Q out crossing the boundary of the heat exchanger?
yeah.
So like here, if you have any value for Q entering
No.
or leaving?
Not given, but it's changing temperature, isn't it?
Yeah, but this is inside. Yeah, I agree with you. It's inside the heat exchanger, but from outside, I'm talking about the outside.
Oh, no.
Nothing, right? So we can also eliminate these two parts. And if we assume that the heat exchanger, the inlet and exit at the same Z, same height. So is there change in potential energy in and out? What do you think? Faisal?
No, sir.
Thank you. So we can also eliminate this. And any information about the velocity in and out? Melih, Tariq?
Yeah, no, sir.
Correct. There's no information about the velocity in and out, so also I can remove this. As you can see, the only part then delta H. So we can say M1. So let's say if I can MW delta H will equal to M refrigerant. I'll put it as R delta H. Mean the change in enthalpy of the refrigerant and change of enthalpy of water multiplied by the mass flow rate of the water. This is what we have from the equation, correct? So basically, this is what we have. So this is the equation that I will use at the end. As you can see, this is the way that you can reduce the energy equation or first law equation or energy conservation equation to a simple form based on the information that you have in the question. All right. So as you can see now, the first requirement in this question is to find out the mass flow rate of the water. Yeah, I know the mass flow rate of the refrigerant. It's already given in the question. And delta H of the refrigerant, I can find the H in and out based on the pressure I have. I have the pressure 1 megapascal. I know the temperature. I go to the tables of refrigerant 134A at superheated condition, and I can find the H value of of the inlet and H of the exit. Yeah. Same thing with the water. Delta H of the water, I have to find H of water because it's liquid water. So it's HF. I know that it's not steam, it's only water at high pressure. So it's liquid. So I can go to saturated liquid tables, and at 300 kilopascal, I can find HF for inlet and HF for exit. And I can substitute. The only unknown part here is the m dot water. I don't know. So I can solve this equation, solve it to find m dot water. Okay. This is in brief. And so let's go and show you the steps of the calculation. But any question before we move? Because this is really very important. You need to understand the steps of calculation or steps of solving this kind of questions. So please, if you have a question, let me know now. All right, so I'll assume that you understand what I'm talking about here. So let's go to the steps of the solution. So as we said that to apply mass balance, as we mentioned before, mass conserved. So we have mass flow rate in must equal the mass flow rate out, no matter how many input and how many outlet, but the total input mass must equal the total exit mass. Okay, so this is we know this from mass balance, and that's why we can say the mass flow rate of water inlet and exit the same, and mass flow rate of refrigerant inlet and exit will be the same, right? So it's here given m.3, m.4 is for the refrigerant, and m.1 and m.2, this is 1 and 2 for the water. All right, so these are given. The only thing we don't know is the m.water. So now the second step here, sorry. we said that we can apply energy balance, and then we end up with this equation, as I may show you before, how to find this equation. All right, so we can remove all the other parts. The only part that we have to consider is the enthalpy, delta enthalpy, change in enthalpy of the refrigerant and change of enthalpy of the water. So we can solve the equation to find m dot water here after we find the value of enthalpy. So this is the task maybe you need to do it yourself after the lecture. You need to find out the enthalpy of water, enthalpy of refrigerant. It's very important here because if you don't practice now, practice yourself how to find out these values from tables, then it will be very hard for you in the exam to find it. And then the time is really limited. So if you have not practiced this before, then you're gonna take a long time, and then you will not be able to finish solving these questions. So please try to practice this yourself after the lecture. So now, as you can see, we can refer to table A4, and at temperature 15, I can find HF value, and at temperature 25, I can find HF2, or the exit value and the enthalpy of the water. So now I have inlet and exit value of the enthalpy for the water. Also, the other way that you can do it is you can use the equation we mentioned last time, the specific heat equation. You can say enthalpy is specific heat of water multiplied by delta T of water. Yeah, okay, that's possible also. You can do it this way. But if you don't want to do it this way, then just refer to the tables. Okay, and then the other side, we need to find out the enthalpy of the refrigerant. So the enthalpy of refrigerant, we have to, again, refer to the pressure and temperature. And because we know it's superheated vapor, we can directly go to table A13 of the refrigerant, and at 1 megapascal and temperature 70, we can find H inlet of the refrigerant. The same thing we can do at the same table, we can find H4, which is equivalent to HF at 35. You know that this is liquid, because the idea here in the heat exchanger, we are condensing the refrigerant. So the refrigerant comes in high temperature and pressure. We want to condense it. That's why they call it condenser. We condense, change the phase from steam to liquid, the phase of the refrigerant, so that we can pump it or compress it back again to the cycle, refrigeration cycle. We'll come to this later on because this is a different topic. But that's why we have to find HF from table A11. All right. So now we have the inlet and exit enthalpies. Simply, you just need to substitute in the equation, energy equation that we reduced, and then find out the m dot water. Now, if you multiply this m dot water with the change in enthalpy, this will give you the amount of heat exchanged, the amount of heat transferred, because this is the second requirement of the question. In the second requirement of the question, they ask you to find out here, if you go back here, the heat transfer rate. And heat transfer rate, as I said, you can use the amount of heat, this one, the water flow rate multiplied by delta H, or you can say the refrigerant flow rate multiplied by delta H. of the refrigerant. Same thing, you get the same answer because they are in balance. Okay, so this is the answer of the solution of the example. Any question before we move to the new topic, please? Any question? Right? Okay. Okay, then. Now, the topic of this week is, maybe I can say this is the last topic in thermodynamics, because now we are week 6, and this is the last topic in thermodynamics. Week 7, we're going to start heat transfer section. You remember before we mentioned that in this unit we have thermodynamics and heat transfer, and this is really a very big topic. Most of the courses they study thermodynamics by itself, and then there is another course related to heat transfer, because there are so many things to cover. But because they are combined now, we are trying to give you the major topics, or the most important topics in both sides. So the last topic in thermodynamics relates to second law of thermodynamics. Remember before we mentioned that in thermodynamics we have 2 major laws. We have first law of thermodynamics, which is the energy conservation law. And this, we said that first law of thermodynamics deals with energy quantity, how much energy we transfer, or how much energy we convert from one side to other side. In second law of thermodynamics, we are mostly focusing on the quality of energy, and we'll come to this very soon. So let's start with the second law of thermodynamics, and the major things that we're gonna cover in this lecture. We will talk about the heat engines and thermal efficiencies, and what do you mean by second law of thermodynamics, what's the major statement of the second law of thermodynamics. Also, we will talk about the refrigerators, heat pumps, and one of the ideal cycles in thermodynamics, which is the Carnot cycle. And also, if you have time, we will talk about the new property, which is the entropy. I think you found this property in the steam tables, but we didn't use it before because we didn't have like any information about it. But now we're going to talk about the entropy and tell you how to use this property, or where to use it. Okay. So first of all, give you a brief introduction about the second law of thermodynamics. In real life, any process, we cannot reverse it. So if you think about any process around you, any system, any heat conversion, you will find that these processes, it's irreversible. You can't reverse it back. So for example, if I have, let's say, hot coffee mug, I put it on the table, and what will happen is after a while, there will be heat transfer from the hot coffee to the surroundings, because the surroundings is with a lower temperature, and therefore the heat will be transferred from the mug to the surrounded air. But here, because the air consumed all the heat from the mug, the question here, is it possible to reverse the heat back to the mug without applying any extra energy? The answer is no, because this is the real real process, you can't reverse this type of process. You can reverse back the heat to the mug unless you apply extra energy to do the process. Same thing, let's say for this, if I have a current flowing inside a resistance, as you can see here, and of course, when you have current flowing through a resistance, heat will be released to the surrounding because the resistance will get heated, and then heat will be released to the surroundings. Now, if I get the same heat and try to heat the resistance, would I be able to generate current, the same current? The answer again, no, because we can't reverse the heat back to the same form of energy without losing energy. So idea here is you can't reverse back the process without losing energy. So there is always loss in energy in any process, in any real life process. Okay, same as like here, this wheel system. If I have this wheel system, I put some load here, I'll rotate the shaft here, but this shaft will, when the pedal rotates inside, let's say, a fluid, there will be heat released because we are changing the mechanical energy to heat. The same question, we can't apply the same heat on this pedal and pull the weight upward without adding extra energy or without losing energy actually. Okay, so this is the idea. Any process must have energy loss. So there is no ideal process in real life. Okay, you can't do a cycle of or operation of any system in a cyclic or in cycle operation without losing energy to the surrounding. Okay, so this is the principle of second law. You have to have loss in any energy loss in any process. Okay. Now, in energy or in second law definitions, we require two major parts or two major source of energy. We have energy reservoir, which we call it here the hypothetical body that can supply or absorb heat from the system. Okay, so for example here, large bodies, for example, like water in oceans, lakes or rivers, or even atmospheric air can be modeled as thermal energy reservoir. Why? Because they are too big. No matter how much energy you release to this reservoir, the temperature of the reservoir will not change. So like put it again here in this form. If I have, this is, for example, a lake, okay. This is the lake, and the lake at temperature, for example, 15 Celsius. All right, and I have a mug of water, hot water. This hot water at 100 Celsius, for example. And I pour this water inside the lake. Would this amount of water change the temperature of the lake? Can someone tell me?
No.
No, right? Why? Because it's the amount of water here compared with the mass of the lake is very small, very tiny. And therefore, even if it's 100 Celsius, when you add it to the lake, the temperature will remain 15 Celsius, to not change. That's why we can call the lake thermal reservoir, because it doesn't change the temperature no matter how much amount of, like, how much energy we add to it from any source. The lake temperature will remain the same. So we call it a reservoir, thermal reservoir. Okay, same with the ocean or rivers or atmospheric air. The atmospheric air will not change if you put hot mug inside the room, because it's the room space or the room volume compared with the mug volume, it's very small. Okay, so as we mentioned here, the reservoir can observe the heat or can supply heat. So we can call it heat source or heat sink. So if it's observing heat, we call it heat sink. And if it's supply heat, then we call it heat source. Okay, so that's the idea of the reservoir. If the reservoir observe heat, we call it heat source. He called heat sink. And if it's supply heat, then we call it heat source. Okay. Now, again, we can give you a very simple system to represent what we already mentioned about the second law. And we said that because we said that in second law, we always say that there is loss in heat or loss in energy in any system. We cannot expect to get output similar to the input. Okay, so for example, this system here, if I want to move heat from this part to this part, I have to apply work in a, let's say, a compressor. There is a fluid passing through this, this fluid works as conveyor to the energy. So it will take the energy from this part, lower part, and move it to the other part and throw it in this sink. In order to do this process, I have to add work. So what happened here, to complete this process, I always lose QH. QH represents loss because I'm moving the heat from one side to other side, but I need to provide work. So that's why, so this is an example of second law of thermodynamics application. So in second law of thermodynamics, what states here, it's impossible to construct a device that operates in a cycle and produce nothing more than transferring heat from one side to the side without providing work. It's impossible unless we do this, what we have here in this diagram. We have to provide work. So this is this kind of system, we call it a refrigerator or air conditioner. The air conditioning system operates based on this fact that we are moving heat from one side to other side, from the low temperature to the higher temperature side by using a refrigerant fluid. And this fluid moves in the system by using external work, which is the pump or, sorry, the compressor. The compressor requires electric power. So the electric power represents the input energy or input work to the system. Okay. Same thing with the heat engine. So now we have air conditioning system. Also, we have heat engines. Heat engines works in opposite way. In the heat engine, we are producing work. So an example of heat engine. Can you give me an example of heat engine, please? Anyone? Can you give me an example of heat engine?
Petrol engine, diesel engine.
Yes, perfect. Thank you, Faisal. So petrol engine, diesel engine, in general, any vehicle engine is heat engines. So what we actually doing in the heat engines, we are providing heat source. So heat source, it could be any type of heat source. So let's say in the vehicle engine, what's the heat source in the vehicle engine? What's the vehicle source in heat engine? For example, Abdulaziz?
Yes, doctor.
So what's the heat source in the vehicle or the car engine? What's the source of heat in the car engine? From where do we get the heat?
From the combustion of the petrol.
Yeah, correct, from the combustion. And the combustion is due to burning the fuel, right?
The combustion generates the heat.
Yeah, correct. So the combustion actually, because we are burning the fuel inside the engine. So this is the source of heat. So without this source of heat, we cannot operate the engine. So this is the source of heat to the engine. So part of this heat converted to work that makes the car moving. The other part must be rejected to the environment. Can you tell me what's this part of energy rejected to environment, where we can find this? Any idea?
The heat has to escape somewhere.
Yeah, exactly. But where is this in the car?
The exhaust.
Yes, perfect. So the exhaust is the heat removed to where? To the environment. So the exhaust actually removing the remaining heat from the engine to the air, correct? And there is other source of energy sink in the engine, that is the heat removed to the cooling water, because also there is cooling water in the engine, remember? So we remove part of the heat to the cooling water also. So there are two parts actually. One of them to the surrounding air, and the other one to the cooling water. But both of them actually at the end will go to the surrounding air, because cooling water will be cooled by the air again. But just to show you that we have to remove heat to the surroundings in any engine. You can't ignore this. You can't say, oh, okay, I can design an engine by just removing this. All the energy from heat source, I can do it, convert it to work. This is not possible. This is wrong. Okay? So this is not possible at all. So that's the heat engine principle. And we mentioned all these things. Okay, so let's talk about a very big heat engine, a mega heat engine. Like we mentioned that there is the car engine is an example of heat engine. There is another example of heat engine, which is the power plant. As I remember before, I think I explained this before. The power plants generating electricity that required to to operate our daily life devices. So these power plants actually located away from the major cities. You can see it here, but if you, let's say, going to, for example, from Sydney to Newcastle, you will find a couple of power plants there. And this is shown in the figure here. this is how it looks like. These chimneys, if you can see these chimneys here, these are the chimneys of the boilers. So we have a furnace, we have here, let's say in this plant, we have 4 furnaces, each furnace connected to a boiler. So we are burning fuel inside these furnaces to heat the water inside the boiler and convert the phase of the water from liquid to superheated steam. Okay, so this is the first thing. This is the furnace, how it looks like. So as you can see, we burn the fuel here, and then the hot gases come through loop of tubes containing water inside to generate steam, and then the remaining gases released to the air, as you can see here in the plant. All these are the gases released from the power plant, from the furnace. So we can say that part of the energy released to the environment or to the heat sink, correct? So this is, again, this is requirement for the thermal engine. So this is first thing, we have boiler, and also we have, after we generate the steam, we can convert the steam, send it to another device, which is the steam turbine. So this is how it looks like in this figure. These are big steam turbines. Can you see this man next to it? These 2 workers next to the turbines, the size of the worker compared with the size of the turbine, they are huge components of the power plant. These devices actually produces the required work to generate electricity. Okay, so the turbine will rotate a generator, and then generator will produce electricity. So this is the steam turbine. And the last one is the heat sink. So the heat sink, as you can see in the figure, in the lower one, this one here, you can see there's a lake. So we can reject heat from the turbine, from power plant. When we condense the steam, we need to reject the heat. So reject heat either by using water from the lake, or we can use what we call cooling towers, air cooling towers. These cooling towers reject heat to the air. So we have two types of devices or components here. Either we use the water from the lake or from a river to cool or to reject heat to it, or we use cooling towers. These towers are actually huge, as you can see, it's very big towers, and the air coming from underneath these towers go through the towers and leaving from the top. And in the other way, we spray water inside, the coming water from the condenser. We try to spray it inside these towers to cool it down by air. So when we cool down, we collect the water with lower temperature at the lower part of the towers. Okay, so it's quite, a bit complicated operation here, but just to give an idea about the steam power plant. So if you see this in the future, you understand how it operates, at least in general operation of this plant. What are the requirements of these plants? So any question before we move? Any question here? Okay, so now what's the, how to measure the thermal efficiency of these systems? How to measure the thermal efficiency of an engine or thermal engines in general? So let's say if we have a power plant like this one, how do I measure the thermal efficiency? you know that efficiency in general, we mentioned before, efficiency is the output divided by the input. This is the general definition of efficiency, output divided by input. Okay, so now if I want to extend this, the output here is the work from the plant. But because the work of the plant not completely converted to output, because some of the work I needed to operate the pumps inside the plant, you know, there are few components in the plant requires electricity, such as, let's say, pumps. We have, let's say, lights. We have, let's say, for example, devices, measuring devices require some power. So we can take the power from the turbine to run these devices, and whatever remained, we can say this is the net work, W net. Okay, so then therefore I have to subtract this internal work from the turbine output. Okay, so here the work of the turbine, as you can see, is represented by work out minus work in, or it's same, you can say it's Q in minus Q out, because the system under balance, energy balance, we can do the same thing using the heat in and out. So we end up with thermal efficiency here. Thermal efficiency is net work output divided by the heat input. So the heat input, you can see here, the heat input is coming from from burning fuel in the furnace. So I know the Q in and I know the work net. I can find thermal efficiency of the system. So that's simply Q work net divided by Q in. And if I want to substitute work net with these two values, I end up with this efficiency equation. All right. Any question? All right, so that's the thermal engine efficiency in general. We can apply this efficiency not only on power plant, on any thermal engine, whether it's a car engine, a vehicle engine, a power plant, any type of engine. Even you can say, because of thermal efficiency, we can say it's the output can be represented in different type of different form of energy. Any question? Okay. All right. So that's, you know, if I want to represent this on a diagram, temperature, volume diagram, or temperature, entropy diagram, doesn't matter. So that's a process of Q in, the Q added on a pressure, constant pressure line, and then there is a Q out, which is the energy removed to the heat sink, which is the river or to air, surrounding air. Okay. But quick practice on energy, on thermal efficiency. Can we work together on this, please? Everyone, do you have a scrap of paper, and we're gonna work on this? Imran, do you have a question?
Yep.
Yeah.
No, I don't.
Okay. So just quickly, this is an example on heat on a power plant. So heat heat transfer to a heat engine from a furnace at a rate of 80 megawatts. So I have a furnace. I know that the heat is 80 megawatt. All right. If the rate of waste heat rejected to a nearby river is 50 megawatts, so we're rejecting heat to a river. The rate of this heat is 50 megawatt. Okay, so this process, of course, will produce output. We don't reject heat for nothing. So this is a here river. I'm rejecting this to a river, but in return, I'm doing something here. I'm not just adding heat and rejecting heat for nothing. I want to generate power from this engine. So the net power from the engine output. This is what I want actually. I need output from the engine. Okay, so determine the net power output and thermal efficiency. So what's the output?
It's gonna be 30, 80 minus 50.
That's right, very simple. So straightforward. So output is always in input minus what we rejected to the surroundings. Okay, so power output is simply the Q dot of high temperature source, which is the furnace, of course, here, 80 megawatt, minus the lower temperature thermal reservoir, which is lower, the sink, thermal sink, heat sink, which is the river. So we are rejecting 50 megawatt to the river. So simply, if I say 80 minus 50, this will give us the amount of work generated from this process. Now, if I want to find the efficiency, what's the efficiency definition? What's the efficiency definition, Imran?
Yeah, it should be.
So what's the general definition of efficiency? We said it is
Input, output by input at 100%.
That's right. Output divided by input. Correct. So the output divided by input. So the output here, we already found it. This is the output. And the input is the heat transferred from the furnace.
So it will be 80.
Yes, correct, 80. So just divide 30 by 80 and then you'll get the efficiency. So that's very simple. So that's so this is actually the thermal efficiency of the system. All right, so it's straightforward actually. Just need to know what's the output, what the input, what the heat added, what's the heat rejected, and then from that you can find out the output. All right, so it's really very easy, quite straightforward. Any question, please? All right. Okay. Still have time. Good. Now, from these definitions, we end up with the what the second law of thermodynamics states. It is what we call Kelvin-Planck statement. So we mentioned this, but we need to repeat it again now and put it in a statement. It is impossible for any device that operates in a cyclic or in a cycle, we might in a cycle mean that it's impossible for any device to operate continuously, like the engine, the car engine. it's impossible to operate the car engine continuously by receiving heat from, let's say, fuel without rejecting anything to the environment. Okay, such as this drawing here. This drawing is impossible. Why it's impossible? Abdulaziz, why is it's possible to provide 100 kilowatt and produce 100 kilowatt? Something missing here in the drawing.
Sorry, sir, what's your question?
Why this drawing is impossible to apply in real life? Something missing here.
Yeah, some of the, sir, there may be a release of some heat energy or energy.
Yes, because here it says QL is 0. You can't do this, and you can't operate an engine without losing heat to a heat sink. You must lose
So,
heat.
that means we don't have any work or the heat transfer, something like this.
No, we have work, but not all the heat coming from this side goes to work.
Because I don't understand this point.
Yeah. Okay, maybe. So now, not all the heat provided by a thermal energy reservoir can be converted to work. Part of it must go to heat sink. Okay. So for example, if I have 100 input kilowatt, there will be, let's say, 30 kilowatt going to the sink or to the surroundings, and the remaining 70 kilowatt is the work output. There must be heat loss. Okay. Clear? Okay. So now, so far we talked about the efficiency of thermal engine. We have something similar to the thermal engine. We mentioned this before, but we repeat it again now. We have two types of engine. We have thermal engine to produce work, to produce power from it, and we have what we call refrigeration system or heat pump system. This system convey energy from one side to other side by using work. So in refrigerators and heat pumps, we are consuming work. As you can see, this work is represented by the electricity consumed by the compressor. For example, in the refrigerator at home, you have a refrigerator. The refrigerator operates by consuming electricity required to operate the compressor of the refrigerator. So there is work, but here work input, not output. Why we provide work here? So in order to be able to convey the heat or energy from inside the refrigerator to outside to the air by circulating the refrigerant fluid inside a cycle, refrigeration cycle. Okay, we will come to this in details, but this is the refrigerator principle. Okay, so how to find the efficiency of refrigerator? Something similar to the thermal efficiency of the engine, but the output is different, of course, because we don't produce work here, we consume work actually. So the required input you can see in the equation here is work input, because this is our input. The electricity is our input. We are consuming electricity. So we should put it as input, correct? But the output of, or the required output, desired output of the system is the amount of heat we want to move from inside the refrigerator to the room or to the surrounding air. So our target here is QL. We are moving heat, right? We are not producing work. We are moving heat or producing heat or moving heat from inside the fridge to the surrounding air. So this is our output. And therefore you will find that the efficiency of the refrigerators or air conditioning systems is different from thermal efficiency of engines. It's higher. And because it's higher, they don't call it efficiency anymore. They call it coefficient of performance. So they call it COP, coefficient of performance. So coefficient of performance of a refrigerator with the simple R here, COPR, is heat or desired output, which is QL, the amount of heat removed from the inside the fridge, divided by the input energy, which is the work of the compressor. Is it clear for everyone? Yeah. Actually, this is a big topic, but as I said before, we will only talk about general application. We'll not go into details how the phase change inside the compressor or inside, sorry, the refrigeration system, because we can describe this on this diagram. If you can see the diagram here, the TS diagram, this diagram shows the cycle on thermodynamic charts. But again, you are not required to memorize these charts because it's complicated and you need more work on it. So, but if when you see these charts, you understand at least this is the cycle of refrigerator system, okay, or air conditioning system. The same thing I mentioned, I'll show you before, the cycle for the power plants. Yeah, this one here, this cycle represents on the thermodynamic cycle chart. This is for power plants. So we have one for the power plants, and there's similar thing, but for the refrigerant, this is for refrigerants or air conditioning cycle. So don't get confused with these two graphs. Everyone has its own system. Okay, so as we mentioned, so we're going to call it COP, the thermal efficiency of refrigerator, and same thing we did with the thermal efficiency. We can say the work net, basically it's QH minus QL, the heat released to high temperature minus heat removed from the low temperature side. Okay, and if I substitute these values in the equation here, if I substitute this in the work net, I can reduce the COP to this equation. All right, as I mentioned before, all these formulas will be given in a formula sheet in the exam. You don't need to memorize them, but I strongly recommend you to understand how to apply these equations, because again, if you have the formula sheet in front of you, but you don't know where to apply these equations, it's going to be hard for you. So please try to understand these formulas and have an idea where to apply this and how to apply it. Okay.
So is that QH
Yeah.
divided by QL minus 1?
Yeah, so this is as a bracket, yeah.
Okay, all right.
Yeah, okay. So it'll be in brackets so you don't get confused with this, yeah. Because what happened here, I took this QL down. Sorry. Show you. We take this Q down here and down here. So I'll put QL here and QL here. Okay, so this can be removed. Sorry. All right, so this is I can remove this part. This will be 1. And the other one, QH by QL, will be in brackets. So be 1 divided by QH by QL minus 1. Okay, Melvin?
Yep.
Right. All right. Let me see if I can give you yeah, let's just do this first and then we go to Kahoot exercise. Just quickly, because we mentioned here, this is the refrigerator equation or efficiency of refrigerator. Same thing happens with air conditioning system. The refrigerator, of course, the temperature of the refrigerator is much lower than the air conditioning system because we have a freezer inside the refrigerator and this temperature maybe drops down to -0, of course. So, but while in air conditioning system, we don't have -0, we have, let's say, something suitable for human temperature. So the temperature, let's say, of air conditioning system, for example, between 18 and 22, while refrigerator goes sometimes below 0. So, but the cycle is the same cycle. The only thing, the difference here is the pressure will be different in different parts of the pressure, of course, and temperature in different parts of the system or the cycle. For example, this is how it looks like the refrigerator in your at your home. This is very simple design of refrigerator. As you can see here, we have the compartment inside. Inside the compartment, we put all our food. And part of this compartment at the top, there is what we call the freezer. This is the lowest temperature inside the refrigerator. So, but the idea here is to take the heat from all the food inside the refrigerator, transfer it to the refrigerant inside the compartment. There is a tube network or a net of tubes inside the refrigerator. The heat transferred to the refrigerant, and the refrigerant takes the heat down to a compressor. So this is the compressor that requires electricity. This is the work input here. We need work input to operate the compressor, and then compressor compressed the refrigerant in a condenser. As you can see, the old design of refrigerator, you can see this condenser like a black mesh of tubes at the back of the refrigerator. I think you noticed this before, or you've seen this before, the black mesh behind the refrigerator. This is the condenser actually. This is where we reject heat to the room. So if you put your hand or try to measure the temperature here, you'll find very high temperature, probably sometimes reach up to 50 or 60 Celsius. It's quite hot. So, which means that we are removing the heat from inside to outside by compressing the refrigerant in the cycle. And then after that, after we release the heat, this is the QH, and this one here, QL, inside the refrigerator, QL. So after we remove QH to the environment, we can take this back, take the refrigerant back to the inside the refrigerator and do the cycle again. Okay, but this is in brief how it works. Any question? Because we're gonna go to Kahoot very shortly and apply this example in Kahoot. So now you know that QL, where is QL here? QL is the heat at lower temperature side, the heat that we removed from the compartment, from the fridge, inside the fridge. And QH is the heat removed to the surrounding air. And W input is the amount of work required to run the compressor. All right, so these are the three major components of the energy balance in the refrigerator. So if you know these, you understand these, then it's quite easy for you to solve any problem. So this example here, food compartment of refrigerator, we know the temperature here at 44 Celsius. We are removing heat from it in a rate of 360. So now 360, what is this? What's the 360 kilojoule per minute? Is it QL or QH? Bakhtiar?
QH.
So just please read it carefully. We maintain the refrigerator at 4 Celsius by removing heat from it at a rate of 360 kilojoule per minute. So from inside.
So the inside, the QL.
QL.
Yeah.
Correct. And again, so if the required power input to the refrigerator is 2 kilowatt, so this 2 kilowatt, which side or which
The
part
WN.
of WN, correct. So this is WN. Now when we know that the power input is the only power input to the refrigerator is coming to the compressor from electricity. So that's work in, correct. Right? So this is very simple but practical example. We will go to Kahoot and try to solve it through Kahoot, okay? If you have question, let me know now, please, before we move to Kahoot. Do you have any question in general, please? All good? All right. So let's then move to Kahoot application. Okay, I need you all to be in Kahoot, as I mentioned before. I'll take attendance based on this. Sorry. All right. Then right, so I'll take the attendance from here. So we have William
Yes.
and Janchi,
Yes.
Bakhtiar,
Yes.
and we have Abdul Aziz,
Yes, sir.
Imran,
So
Tariq. This is your all of you. This is your actual name, right? Because I'm gonna go to the attendance sheet and search for your name. So this is your name, right? First name.
Tariq is my second name, actually. It's my
Yeah,
middle name.
but it's in your
Yeah,
full
yeah,
name. Yeah.
Yeah, yeah.
Good. Thank you. And Mervin. Mervin.
Yeah, I'm here. Just my mic
So
was
we
muted.
have 1, 2, 3, 4, 5, 6, 7. We have 7 only. Okay, Faisal. Okay, good, Faisal. Faisal, and anyone else didn't join us? Right, let me check this, how many students we have here. So it's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have 8 students. Yep. Okay, good. So now let's start. We'll start it's the same refrigerator question. So we're gonna start with the first question. Okay, so we have fridge heat removing at 360 kilojoule per minute. What is the desired output QL? You need to convert minute to second. So you need to get it in kilojoule per second. So you need to divide by 60, correct? Because it's minutes. We said that QL is this one. Still one missing, didn't answer. Straightforward. Okay, good. Thank you. So I think it's quite easy. Just divide by 60, you get the amount of QL, the amount of heat removed from the compartment inside the fridge. Okay, so that's the first one. Jengshi in the lead now. Second, what do we need? What do we need the compressor in? Why do we need the compressor in this region? Why do we need this compressor here? Just be careful, read it carefully, because the idea of the compressor is to pump heat from one side to other side. So we are taking heat from this side, move it to the outside. So this is QL, it's QH. So the compressor is doing this job. Okay, so in the compressor, actually, we pump the heat from inside to outside. So,
But the compressor is actually compressing the liquid, is it not?
yeah, compressing the refrigerant, but it works as a pump, heat pump, to pump heat from one side to other side. So we are taking heat from inside the refrigerator, pump it. I know the term, or the term looks weird, like how do we pump heat? But this is what they agree to call it, a heat pump. Same like, let's say, water pump. We're pumping water, and also we pump heat from one side to other side. Yeah, just
I
like.
thought it was compress the liquid because it's called a compressor.
Yeah, that's right. I agree with you again. But we don't have liquid, actually. We have gas. We don't compress liquid, we compress gas, correct? We mentioned before. In liquid, we pump liquid and we compress gas. So here, I know that you look to this answer, compress the liquid, but again, it's wrong because we don't compress liquid. We compress. If I say compress gas, I agree with you there. This is can be another correct solution or correct answer. Because
So the liquid is pumped, right?
Yeah, the liquid we pump, we use the pump with the liquid. With the gas, we say compress the gas. Yeah. Okay, no problem. Let's continue. Okay. Third question. What is the COP equation of this refrigerator? Remember COP equation? COP equation, we said the desired output. So what do we need here? Which output here? We need to remove QL. This is our output. Divide by the input. So which one of these is correct? Yeah. Yeah, correct. So this is the output is our QL. The input is the work provided by or supplied to the compressor. Yeah, correct. Okay. Any question about this? Okay, still Jiangxi in the lead. Number 4. If the required power input 2 kilowatt and heat removed is already given, what's the COP? So remember, COP is QL. We said output divided by input. Make sure that you convert the units. Yeah. Just to give you a clue here, COP never be like this. Of course, COP doesn't have units. So if it's kilowatt, then this is wrong immediately because it doesn't accept units. COP is ratio of energy. But if you see COP in this, like these numbers, big numbers, COP doesn't reach these numbers. Actually, COP then never exceed probably, never exceed, for example, 4 or 5. It's like in a practical life, you can't find COP more than 4. Okay, so for the future, if you, let's say you are doing calculation and suddenly you find COP 180, this is wrong because you can't get 180 at all. Just to give you like a clue for the future tests or exams. Okay, but yeah, it's good to know now. Okay, any question? Right, so, right, the last question. The total rate of heat rejection to the room. So heat rejection to the room, which is QH. So you know QH here, sorry. You yeah. Yeah, there's a mistake here in this question. It should be QL, not QH. This is should be QL. This because you add QL, so QH is equal to W plus QL. So you add 3 plus 2, you get 5. Yeah. Yeah, sorry for this, but anyway, just this is a practice for you. But yeah. Any question about this?
Thank you, sir.
Yeah. Okay. Yeah, idea here because we are trying to interact with each other and try to get proper knowledge about the topic. It's not a race. It's not just it's like a game. We kind of fun. So we have Tariq in the first, the third one, Merv in the second, and Jamshi in the first. Thank you everyone for your contribution in this. I really appreciate it because this looks like it shows that you are focusing on my lecture. Okay. All right, so let's do this now, finish. So that's in brief. So all the information, same as we did in the Kahoot. So exactly the same, just go through it and you'll find out the answer. Now, we continue with this. Remember, we mentioned that pumping heat. So pumping heat inside the refrigerator. So efficiency of heat pump, we call it heat pump. If we are pumping heat, then it's gonna be heat pump, right? So in refrigerator, COP refrigerator, we know that our desired output is the QL, the amount of heat removed from inside the compartment. in heat pumps, for example, at home, if you have an air conditioning system, you know, the air conditioning system, either split unit or window type unit. In the window type unit or split unit, what actually we are doing, this is of course the space inside the house, and this is outside. Okay, so we are taking heat from outside, pump it to inside. It looks weird, right? Because normally we do this process in winter, and in winter time, the outside temperature, for example, 10. The inside temperature, for example, let's say 20 or 21. Look, how come we transfer heat from lower temperature to higher temperature? That's why we call it pump, because what we do here, actually, we are using the compressor W, trying to compress the fluid, the gas inside or the refrigerant gas inside the air conditioning system, and pump the heat from outside to inside. And somebody will ask, like, how can we pump heat while it's not heat, it's 10 Celsius? The answer is because we have heat source, the amount of heat source is huge. Like the air outside the house, the ambient air is, massive. And we're trying to get the massive energy, even if it's at 10 Celsius, we are trying to get heat from this air as possible as we can, and take this amount of heat by using a refrigeration cycle and take it to inside the house to heat the house. So it's gonna be like, when you think about it in the first time, you find it's impossible, but we'll show you on the cycle, because we are doing change, we do the phase change. When we do the phase change, we are changing the phase, let's say, or the refrigerant from gas phase to liquid phase. We mentioned that before. When you change the phase from gas to liquid, you release heat, and the vice versa. You change from liquid to gas, you consume heat, or you take heat, right? So what we do here, actually, we are changing the phase of refrigerant from gas to liquid inside the house, so that we can reject heat inside the house and keep the temperature of the house at 21 Celsius. So we'll come to this in detail. But as a principle, I think it's should be, you should to make it clear now for you. So again, in the heat pump, COP, we have the same thing. We use the COP because we are using refrigerant, but we call it COP HP. Remember, before we call it COPR, representing refrigeration, right? Now we call it COP HP because the desired output has been changed. Before, the output was QL, right? But here, the output is QH. So that's the difference. This will change the value of COP. So now QH divided by work net. Okay? Do you follow me, everyone? Do you understand what I'm talking about here? Yeah. Okay. Right. Okay. So same thing we do. we can substitute the value of work net by QH and minus QL, and we end up with this equation, the equation of the COP. This is the equation of COP. It's QH divided by QH minus QL, or if you can reduce it, take QH down in the denominator, and then you'll end up with this equation. So you can use either one of them. You can use the first one or the second one, doesn't matter. Both of them will give you the same results, right? Okay. All right, we have other definition here in second law. As we said before, the second law is the real life process of any device, and because it deals with the quality of energy, as we mentioned before, energy cannot be reversed in a cycle without applying applying work. So therefore, we always has irreversible process in real life. So a reversible process is defined as a process that can be reversed without leaving any trace or without losing any energy. While the irreversible process, which is the real life process, the processes that are not, which are all processes are not reversible, called irreversible process, which is the real case in our real life application. So all the real life application or real life process are irreversible processes. Okay, and we can have so many examples. If you have frictionless pendulum, for example, you have this pendulum, put it in a vacuum, and there is no friction at all, then this pendulum will stay moving and like in unlimited time, because there is no friction, and it's reversible. When it goes from one side to other side, it will return back to the same side, because there is no losses. Okay, same as with other application in our life. Okay. And reversible, there are two types of irreversible. It's internally and externally, or we call it total irreversible or total reversible. So a process is called internally reversible if no reversibilities occur within the boundary. So we have, let's say this one is a boundary here. There is no change in temperature in any point of the boundary with inside temperature, then it will be internally, we call it internally reversible system. And totally reversible when there is no difference between this with the surroundings. The surroundings at 20 and inside 20, then we call it totally reversible, because actually the heat is not moving, it's not transferring in massive amount. It's slight change, like 0.0001, which is negligible. So the heat is not transferring actually in big amount, very, very limited amount. Okay. Okay, what we need to get from all that we mentioned so far, we need to compare our systems with an ideal system. So to know that whether your system is doing well or not, how do you know that this system is efficiency of the system is, it's fine for me. It's okay for me. It is efficient. How do we know it's efficient? We need to compare it with an ideal system. And this system called Carnot cycle, which is reversible cycle. So we are comparing our cycle, our system with, or our system operation with something ideal, which is reversible cycle. As we said before, reversible process is an ideal process. So if you have a complete cycle of different processes, then this is the ideal cycle of our system. And we compare the actual efficiency of the system with the ideal cycle efficiency, which is the Carnot cycle. And the Carnot cycle or Carnot heat engine has 4 processes to complete the cycle. It's 4 processes, all of them are reversible, but there are 2 expansion here and 2 compression. And I will show you on the diagram because it's hard for you to understand without showing it on the diagram. So, but let's just say the current principles, the efficiency of any reversible heat engine is always less than the efficiency of reversible one. So always we have the actual efficiency of any engine is less than the Carnot efficiency or the reversible cycle efficiency. And the efficiencies of all reversible heat engines operating between the same 2 reservoirs, which means that we are operating between the same temperature, high temperature and low temperature. The temperature doesn't change, but this the process or the processes inside the cycle, we are choosing different processes. For the Carnot, we are using reversible cycle, reversible processes, while in the actual one, we have actual process, we have always losses. Okay, so we'll come to this in details. Don't have to worry too much, but just to give you an idea about what do we mean by Carnot cycle. And this is how it looks like on a PV diagram. So this is the y-axis P and the x-axis is V. And as you can see, the first process, process 1, from 1 to 2, from 1 to 2, it is isothermal expansion, meaning that if the piston is moving backward and I'm increasing the volume inside the cylinder, and then after that from 2 to 3, second process from 2 to 3, we have reversible adiabatic expansion. What do we mean by adiabatic? Adiabatic means there is no heat exchange with the environment. As you can see here, there is insulation. So we are isolating the cylinder from the surrounding. There is no heat loss or heat added to the cylinder. So we call this kind of process adiabatic process. Okay. And then after that, we have process 3, which is compression and also isothermal. So we are compressing the fluid at constant temperature. And the last one is also compression, but adiabatic. Okay, so we are compressing the fluid inside the cylinder again back. And then we keep doing this on and on. We call this a cycle. If this keep operating continuously, then we call this a cycle. And this is actually no engine operates without a cycle. So all engines must operate in a cycle. Otherwise, it will not operate. It will not keep going. Okay. So yeah, any question? So this is the Carnot cycle. As we said, this is the ideal cycle for any engine. And we're going to compare our efficiency with this efficiency every time. But how to find the Carnot engine efficiency, we'll refer to the same definition of thermal efficiency. And we said before, the thermal efficiency is this equation. Remember, this equation coming from, we said output divided by input, correct? And said output is W, we can say W is equal to QH minus QL, correct? This divided by, of course, QH. Right, so if I take this part separately, QH divided by QH is 1 minus QL divided by QH. So QL divided by QH, and this is our Carnot efficiency, right? So we'll have this efficiency. We can, because we are working between two reservoirs, hot and cold side of the system, we can replace QL by T. So as you can see here, I have the same ratio. If I divide QL by QH or TL by TH, it will give me the same ratio. Therefore, I can simplify the thermal efficiency, this one, and substitute TL here and TH on this side. And remember, T is Kelvin. So here, T in Kelvin. Just remember this, because if you put Celsius, of course, it will give you a different wrong answer. So make sure that you are using Kelvin units here. All right, so this is the efficiency of the Carnot cycle. You use the temperature, and this will give you ideal efficiency. All right? Any question? So remember, this is Carnot efficiency. Right? Any question? All right, I think we already, the time is already due, right? So maybe I'll leave this, yeah, I'll leave this for next week. We'll talk about the entropy. So next week we'll talk about entropy. We'll finish thermodynamics, and then we start with heat transfer, the same lecture. But if you have any question before we leave, any question, guys, before we leave, please ask.
When's our next quiz?
And next week's quiz will be week 8, so 2 weeks, 2 weeks from now, yeah. But we will do it on thermodynamics topics.
So no heat transfer?
No heat transfer topics. I'll check, actually. I'll see how much we get, how much we do in heat transfer, but we'll focus more on thermodynamics. Yeah.
Okay, thanks.
No worries. Any question, other question? All right. Thank you for attending the lecture, and we'll meet you next week.
Thank you, sir. Have a good day.
Same to you. Thank you.